Hey guys, welcome back to AlgoYogi. We are doing linked list series and we have 3 more problems to go. And our third last problem is insertion sort list. Let's go to the problem on LeetCode. So given the head of a singly linked list, sort the list using insertion sort and return the sorted list's head. And the steps of insertion sort are given here. We already know, I guess. If we are so far into solving LeetCode problems, we would know what an insertion sort is. So let's see how we're gonna solve it. And they have shown a little animation over here how insertion sort actually works. And we will understand it right now. Okay, so basically this is a list. If it were an array, I think that would make our job easier, but as a brute force solution, you can always do that and just convert it into an array, perform the insertion sort, and then just convert that back to a linked list and then return the head of the linked list. Now we are just going to play around with the pointers, and that's what is preferred. That's what gives us the best answer in terms of space complexity. We don't have to use extra spaces to storing the array. So let's get into it. So before we move into that, let's understand what an insertion sort does, and how we basically perform it. So if we are given some values, let's say we have 4, 2, 1 and 3. So in insertion sort, what happens is we have some part of the list we have of these numbers is sorted, and another part is unsorted, and then we pick one element from the unsorted part and place it into the sorted part, but at the right position. How? So let's say this is unsorted part for now, and this is sorted part. See, one element is already sorted, right? So what's going to happen is we're going to pick one element from the unsorted part and we're going to find its right position in the sorted part. So if we check, is 4 greater than 2? Yes, then we're going to keep going down, right? We're going to place it basically before 2, before 4. So this is where its right position is if you compare it with 4. So this is already done. Now we have, this is our sorted part, this is our sorted list, and this is still our unsorted list. And then basically we're going to do the same thing. We're going to place one over here, and then this is done, and then we're going to choose basically the remaining one, which is just 3. So what will happen is we're going to keep comparing 3 with, you can do it either way. We can do it from the beginning. Is 3 greater than 1? Yes, then we move forward. Is it greater than 2? Yes. Is it greater than 4? No, then its place belongs to basically middle of 2 and 3. So now we have this sorted list here. Well, that was just to understand the insertion sort, but that's not how we're going to do it with the linked list. We will do a little differently so that we can play around with the pointers perfectly, right? So initially what's going to happen is we're going to, in our unsorted list, we're going to have a dummy pointer, let's say dummy pointer, which will point to our head. This is our head, and we're going to have something called previous and something called current. So far this is our sorted part of the list. That's what we understood, right? This is our sorted part of the list because it's just one element. Dummy is just for the simply make it handy that when we can return the head of the list, when we're returning the answer. So we can always return dummy.next. Now, if this is sorted part, then we're going to keep checking if this element is basically smaller than my current number. So is this sorted than my smaller than my current number? This is not. Then what's going to happen? We will find right place of this element into the sorted part, which is this. So what really is going to happen is we're going to compare. So first thing first, we're going to place the pointer of prev to basically cur.next. So this reference is gone. This reference is gone. Then we have this 2, and we're going to compare 2 with basically dummy. Maybe we can compare with dummy, although because this element could become the head of our sorted list as well, and in this case it will. So we're going to compare it with the dummy, but not really dummy.next. So I'm going to compare it with dummy.next, and it's smaller than dummy.next, so it cannot go beyond 4. It's going to come before it. So what's really going to happen is dummy will point to 2, so 2 will come here, and then we're going to have this is still current. We are removing it from here, we're placing it over here. This is still current. So what we're going to do is we're going to place cur.next to dummy. Now we're going to call it temp, because it's not always going to be dummy, but we're going to have a temporary pointer which will point to basically dummy.next, and then this cur will point to that dummy or temp. Temp will be somewhere here, temp.next, which is this. Now it's pointing over here. Temp.next will basically point to here, and there is some part of the sorted list already here, and there is dummy. I know it's a little confusing, and dummy is pointing to the first node in the list, but if you're following it like perfectly, you should have no doubt like how we're doing it. Smart people study like that. They just do. Sorry, just kidding. I think I'm gonna get better at explaining. Okay. A little bit of insecurity there. But hi. So now this needs to go away, and we're gonna place it back again to prev.next. all right, prev remains for now, prev remains here, and then we're gonna again start basically iterating. And remember, if you come across a right order, it's like 1 2 3 4 5, then these pointers prev and cur, which is right now it would be basically cur will come over here. So is cur over here, prev over here. 2 has been placed right in the front. Okay, so sometime it might happen you come across something like this, like 5, then this is the right order, 2 4 5, it's already sorted, so we will move this pointer 1 ahead. Okay, so let's do that part. That's the easiest part, playing around with the pointers, and then in the end we will just return dummy.next. all right guys, okay, let's code it up, our solution. Now I think a little bit over here, and okay, looks beautiful. So as I said, we're going to create a dummy node. So dummy would be list node. Let's give it value 0, and its next will be head. Okay, now we're going to have something called current, and then we're going to have something called previous. Current will be pointing to head.next, and pre will be pointing to head, just because one element is already sorted. I wish I had them in the other order. I think that would make better sense, but I think you know what I'm doing here. So one element is already sorted. We don't have to start from the head, right? It's already sorted. We're considering it's sorted. One number is already sorted. We're gonna start from the head.next, right? If it exists. All right, then while current, if current dot value, if it is greater than my prev dot value, that means it's sorted. They both elements are in right order. That's how they're supposed to be in a sorted list, in ascending order. Then what's going to happen? We just move the pointers, as I said. So cur and prev will be basically cur dot next, and prev will be prev dot next. All right, and then we're going to continue in the loop to the next two elements. All right, Otherwise, what's going to happen is now we found an element that is smaller than my previous node. So current is pointing to a number which is smaller than my previous node. What do? We're going to place it at the right position in the sorted list. So let's have a pointer to pointing to basically the beginning of the list, which is dummy, and I'm just gonna not point to dummy.next but dummy because it could become the head of the list. It could be something that comes next to dummy. Okay, but what we will do is we're gonna check its right position. So we're checking for the current element. So if current dot value is basically, what I should say is, if current dot value is smaller than temp, I should call it temp dot next dot value, that means this is where it belongs, right? This is where it belongs. And I think might be missing something here. Okay, so what we are actually trying to do is yeah, okay, we're gonna keep checking it. Let's check if this is greater than temp, then I'm gonna keep improving my temp, you know, because we want to get to the right position. We do not want to check the truth here. We just want to check the falsehood of this algorithm, so that we keep moving the temp pointer to the right place. So otherwise, if current is greater than temp, what temp.next is pointing to, that means current doesn't belong here. It maybe next to the temp. So temp becomes temp.next. Okay, temp.next. All right. Otherwise, now we are at a place where temp.next value is basically greater than cur.values. Now that's where this current value belongs, because next is greater than cur. So in a sorted order, current should occur before temp. So what we are gonna do here is, first we forgot something. That's in the beginning, you know, we had this prev dot next was supposed to point to cur dot next. All right, that we should have done it earlier. Doesn't matter, we're doing it now because now we are removing current pointer from the middle of anywhere in the list and bringing it in the front in the sorted part. And here we're gonna point cur dot next to temp dot next. All right, so cur dot next point to temp dot next, and temp dot next points to cur. All right, so that now cur is in the middle of temp and temp dot next, because here we checked that cur is basically lesser than next but greater than temp. Okay, and one more thing, before we move on to the next iteration, let's move current to previous dot next, prev dot next. I think that's it. Finally, we can just return our dummy dot next. That's it. Okay, let's see if we are doing everything correct. So temp is dummy. We are finding the right position for current value. We just keep moving the temporary pointer next, unless we come across where current is smaller than our temp dot next. You know, we're checking the falsehood of the current dot value, and then we just place the next prevs next. We remove the reference of the next from the unsorted list, and then we current dot next becomes the temp dot next, so that we are placing it right in the middle. And then temp dot next is pointing to current, and then current, let's send that current pointer because now we have fixed it into the sorted part. And then finally we return dummy dot next. So let me zoom out and let's basically run it on the examples. All right, let's submit it. Let's talk about the time complexity and space complexity. So we know, like, worst case, what must have happened is we are choosing every element, and it's like completely unsorted loss. It's sorted in like reverse order, you can say. So I'm choosing every single element and I'm checking it every single place, and then I'm placing it basically. I'm sorting it again and again and again. So I'm choosing every element. For every element, I'm comparing it with every other element, which is like worst case time complexity would be big of n square, and that's like a usual time complexity unless you move on to quick sort, merge sort. And space complexity, we know we haven't used any. We're just playing around with the pointers, and that's the beauty of I would say linked list, because these are the blocks of memory, right? Rather than asking for a continuous block of memory, you have these small chunks here and there, and then you just have these pointers connecting, so that it seems like a linear array, linear data structure, but in this whole area of small blocks of memory, you're just pointing here and there, and then you're connecting these dots with next and previous pointers to make this a linear data structure, right? So space, I just wrote the complexity. The space complexity would be big of 1, which is constant. All right, then let's go back to AlgoYogi. I don't know if you can see it. You can see it. So we're gonna mark this solve and see you guys in the next problem. Until then, bye bye.